Hello. Uh, in this video, I'll give you a demo for this linear algebra for deep learning notebook. So you're basically understanding the different components of machine learning, neural networks. So in the first cell, we are just creating a simple neural network. So we have initialized the weights, bias, huh, and we'll be using ReLU for activation. And yeah, this is the linear transformation which we are using, which is just input matrix multiplied by w weights 1 and the bias, so this gives us z1, and then z1 is then passed to a ReLU function, and whatever output we got again will be this is layer 2, so it will multiply matrix multiplied with layer 2's weights and layer 2 bias. And yeah, so huh so this is just a very basic forward pass without any back propagation, just how it looks. So we got x, we got layer 1 layer 2's weight and biases, and this was the output. And it predicted these classes. So now let me yes, so now yeah, there are different norms which we can use. So the first one is L1 norm, which is which uses Manhattan distance, and there is this L2 norm which uses the Euclidean distance, and then we have L infinity norm which uses the Chebyshev. So so basically the unit ball, or the shaded area is the unit ball. The unit ball shows all the points with norm equals to 1. So L1 encourages sparsity, so solutions hitting corners is equals to 0, and L2 shrinks all weights evenly. So yeah, it's just the formula for different norm, how it's Manhattan, this is Euclidean, and then L infinity. Now let's move to eigenvalues and eigenvectors. So eigenvectors are basically, as it says, it gives you it points in direction that the matrix only scales. So it with the values, it also gives you the direction in which the matrix is scaling. So actually the PCA uses this to find the direction of maximum variance. So here you can see there are different vectors, but you can see the red one is going in this direction and the magnitude is less, but the dark green are going in this direction and the magnitude is huge. So you know that this you can find out the directions of maximum variances. So yeah, eigenvectors put in directions that the matrix only scales, and no rotation. Eigenvalues tell you how much it scales in that direction. And PCA uses both to find the direction of maximum variance, and it can be found out using linear algebra eig, and the matrix. It will give you the eigenvalues and eigenvectors, and based on that you can plot it and see the direction of the vectors scaling. Eigenvalues and eigenvectors reveal the soul of a matrix. It's for a matrix, if A matrix multiplied by V equals to lambda multiplied by V. So here V is the eigenvector, basically the direction that doesn't change, and lambda is eigenvalue. I mean, it means how much it scales. So in PCA, in deep learning, PCA, eigenvectors of covariance matrix equals to principal components, and stability is eigenvalues determine if the gradients will explode or vanish, and spectral normalization means control eigenvalues for stable training. So yeah, when you know the how it is going to scale, so you can control it. So it's quite useful. Then we have these transpose, inverse, and determinant properties of vectors. Here, transpose is essential for attention and backpropagation. Inverse is undoes the transformations used in theory, and determinant is measures volume scaling. And yeah. Yes, so this is the determinant. 4 means the area is multiplied by 4. Determinant 1 is area is preserved, just the shape changed. And determinant 0 means it collapsed to a line and lost the dimension. Hmm. Hmm. So determinant tells you how much a matrix scales space. If it is greater than 0, it means it preserves orientation but scales by determinant. If it is less than 1, it means it flips orientation. If it is 1, it means the matrix squashes to a lower dimension, so not invertible. So in deep learning, normalizing flows uses determinants to ensure transformations are invertible. And then we have matrix inverse, which is undo a matrix. The inverse of a matrix satisfies that A multiplied by the in A matrix multiplied with its inverse always results into identity matrix. Identity matrix is all the diagonals as 1 and others as 0. So inverse are rarely computed directly in deep learning because it's too expensive. Instead, we use optimization algorithms, but understanding them helps in theory. So this is the attention scores for the tokens. Again, calculated. Yes. So this is a matrix 2 cross 3. Its transpose will always be 3 cross 2, and the rows will become columns and the columns will become rows. We did this earlier. Yeah, it is. So this is actually used in attention, where scores equals to q q matrix multiplied with k transpose, and q and it's a query key dot product. And also for covariance, where matrix minus mean transpose matrix multiplied by input minus mean divided by n. So the special matrix properties, inverse, transpose, and determinant. Yes, did that. Yeah. So now let's see how the neural network layer works. So this is the input vector, and this is the weights. So these will these two vectors will get matrix multiplied. So as I earlier mentioned, that its columns and these rows should always match for a matrix multiplication, and the output will always be 4 cross 2, or like row into this column. and when we are doing an operation with bias, it's always a broadcasting one. So these values will, broadcasted to we will get, after this we'll get a 4 cross 3 2 matrix. So this is a two these are two values, so it will get, multiply get added to all those 4 cross 2 matrix, and we will get an output like this. Yeah, it is also explaining the same way. Let me just, so yes, so this is a 2 cross 2 matrix, and we are just matrix multiplying it. So matrix multiplication is this value multiplied by this, which is 5 into 1 5, plus 2 into 7, which is 14. So 14 plus 5 is 19. So we got this value. Again, same, 1 into 6, 2 into 8, and we'll get 22, like that. So this is how we get the matrix multiplication done, and why it is important in deep learning. So matrix multiplication is the core operation in neural network. It enables batch processing, layer transformation, and efficient computations. And here it is just explaining why the shape is the shape rule and why it's critical. As I mentioned earlier, that this n should match with this n, and this will then collapse to m cross pre. That is, a condition which has to be followed. And yeah, even here it's 3 cross 3, but this is 3 cross 1, so 3 3, and we got a 3 cross 1 matrix over here. That is just a general rule which has to be applied. Then we have few other matrix operations like matrix addition, scalar per matrix, vector, matrix into vector, matrix. And matrix addition is layer outputs and to skip connection. Scalar into matrix is when we want to scale weights. Matrix and vector is single sample through layer, and matrix is batch processing, which will be in the next section. So element wise product, which is also known as a Hadamard product. Element wise multiplication multiplies corresponding elements without summing. So in deep learning, LSTM and GRU gates control information flow, attention mechanism, weight, value by attention score, and values, cosine similarity,